Hi everybody, Mrs. Pesic here. We are looking at Chapter 4, Exponential and Logarithmic Functions, and Section 4.1 is Exponential Functions, Growth and Decay. Our learning objective, and you do not need to write this down, but just so you know, our learning objective is to write and evaluate exponential expressions to model growth and decay. Alright, so let's start with an example. Let's say that we borrow $500 from a loan shark, and he says that we need only pay back $1 the first day and just keep doubling that each day for 14 days. Well, we may think that we are getting off easy. Let's see how this would play out. On day 0, we would have to pay $1. On day 1, $2. On day 2, $4. Sounds like we're getting off pretty easy right now. Day 3, $8. Day 4, $16, and so on. So maybe we won't have to pay all $500. But wait, we got to go all the way up to day 14. And day 7, it's already doubled to 128. Day 8, 256. Day 9, 512. We paid over $1,000 total so far. Day 10, 1,024 more. Day 11, 2,048, and so on. So the doubling really adds up very quickly, and we would end up paying a lot more than the $500 that we borrowed with that deal from that loan shark. We can model this with an exponential function. The parent function for an exponential function looks like this: f of x equaling b raised to the x power. Now this is very different than any function that we've studied so far, because b, the base, is a constant. So b is a constant, and it's considered the base of the function. But the variable here is the exponent, very different from anything we've done before, and it's considered the independent variable. All right, so overall, if we take a look at this parent function a little bit closer, again, f of x equaling b raised to the x, the b is the base, and the x, our variable, is the exponent. So, for example, f of x equaling 2 raised to the x. That's what we were just looking at. So if we wanted f of x equaling 2 to the x, if we plug in negative 2, that's going to be 2 raised to the negative 2 power, which is 1/4. If we plug in negative 1 for x, we get 2 raised to the negative 1 power, which is 1/2 to the first, which is 1/2. If we plug in 0, we get 2 to the 0 power, which is 1. And 2 to the first is equal to 2. 2 to the second is equal to 4. 2 to the third is equal to 8, and so on. Let's take a look at how this graph looks. If we look at the graph and we type in 2 to the x, 2 raised to the x. Try this on your Inspire, please. If we graph 2 to the x power, the graph looks like this. It's actually starting very, very slowly, and then once it hits 0, 1, it just really takes off very fast. This is an example of exponential growth. All right, notice that as x approaches negative infinity, the function gets closer and closer to the x-axis, but it never reaches it because 2 raised to the x can never equal 0. As x approaches negative infinity, the graph gets closer and closer to 0, but never reaches it. All right, we call the x-axis then, in this case, we call it an asymptote. Okay, the x-axis is called an asymptote. An asymptote is a line that a graph approaches as the value of x gets very large or very small. So here's our parent function for f of x. It's a times b to the x. If a is greater than 0 and b is greater than 1, this is considered an exponential growth function. The function increases as x increases. If a is greater than 0 and b is between 0 and 1, then it's an exponential decay function, which means that the function decreases as x increases. So let's look at a few examples. Let's say we have the function f of x equaling, let's say, 3 times 1.5 raised to the x. All right, my a is 3, my b is 1.5. Since b is 1.5, that means it's greater than 1, which means this should be an exponential growth function. Let's type it in and see. And I want 3 times, and in parentheses, I'm going to put 1.5, close parentheses, raised to the x. Sure enough, it is an exponential growth function. How about this example? let's say that g of x equaling 4 times 0.9 raised to the x. Well, this time, since my b value is 0.9, that means that b is between 0 and 1, so it's going to be an exponential decay. Let's try this one on the calculator. So we're doing 4 times 0.9 to the x. Let me get a new graphs page. So I want 4 times quantity 0.9 close parentheses raised to the x. Aha! So now this time the graph is starting out high, but it is coming down, and the further out we go, we can see it's getting closer and closer to the x-axis, but it's never reaching it. So this is our exponential decay function. All right, let's take a look at this. So tell whether the function shows growth or decay. So for this one, f of x equaling 10 times 3/4 to the x, since 3/4 is between 0 and 1, our base is between 0 and 1, this is going to be what? You fill in the blank there. How about this example? G of x equals 92 times 1.05 to the x. Since this right here is a number that our base is greater than 1, then this is going to be an example of exponential what here? I'm going to ask you to fill in these two blanks for your notes must do. Please get those examples down. These are going to be your notes must do for this set. All right, you can model a growth or decay by a constant percent increase or decrease with the following formula. So with this formula, we have a of t equaling some number a times 1 plus r raised to the t. The a of t is going to be your final amount. The lowercase a is your initial amount. R is your rate of growth. And t is the number of time periods. And we can say that 1 plus r then, which is everything in this parentheses here, the 1 plus r is your growth factor. This works the same if we want decay. The only difference in the two equations is this equation here had a plus, so it was growth. This equation here has a minus, so it's decay. All right, so if we have a of t equaling a times 1 minus r raised to the t, the r is considered the rate of decay in this problem, and 1 minus r is the decay factor. All right, let's take a look at this idea. If a function increases by a constant rate, like 5% per year, that is the same as multiplying by 100% plus 5%, or 105%. And we can write this in decimal form as 1 plus 0.05, or we could write it as 1.05. That's going to be our growth rate, 1.05 for a 5% increase. If a function decreases by a constant rate, like 11% per year, that's the same as multiplying by 100% minus 11%. Instead of adding, we'd subtract, which would give us 89%. We could write that in a decimal form as 1 minus that 0.11, which is 0.89. So 1 minus 0.11 would be our decay factor, or we could write it as 0.89. All right, let's take a look at this example. We have Clara. She invests $5,000 in an account that pays 6.25% interest per year. Write a model that shows this situation. So to do this, we would write a of t equaling the initial amount, which for Clara was $5,000, and then we need our growth rate, which is going to be 1 plus the 0.0625. We take this number here, that's the percent, and we rewrite it as a decimal, and it's raised to the t power. Okay. Now for part B, after how many years will her investment be worth $10,000? So she's investing $5,000. We're wondering how long is it going to be until it's worth $10,000. To figure this out, let's use the calculator. So we're going to do 5,000 times 1 plus 0.0625t. Let's type this in. Remember, when we type in this equation, we want to raise it to the x, not to t. We never use t on a graphs page. All right, so when I enter this function, I'm not seeing anything. Well, that's because my graph's only going up to like $6, and we know she initially invested $5,000. So let's change the menu window, zoom window settings. I know that I want to start with year 0, for example, and I want to go up to, I'm not sure how many years, let's say 30 years. And then we want to start with y minimum of at least 5, well, I'll say 0 for this. We could say 5,000. And then we want to have it go up to at least 10,000. I'll say 15,000. So there's our graph. Okay, we're seeing what we want to see. And now we can do graph trace, for example. So I can do menu, trace, graph trace. And if I type in, let's say, how much in 5 years? In 5 years, 6.77. How about 10 years? Oh, that's already over. No, it's 9,000. Almost there. So let's try 11 years. 9,700. 12 years. There we go. So now it's over 1,000. We could also have gotten this by going to the table. Remember, you do Control T to pull up the table, and we can look at the table here to see be over $10,000. And we can see that it looks like right about year 12 is when it's over $10,000. Let's look at one last example. A city population which was initially 15,500 people has been dropping by 3% per year. Write an exponential function to model this situation and then graph the function. So to do this, we are going to want to write f of x equals, we want our initial amount, which was 15,500, and we want it times 1. Do we want a plus or a minus? Well, the population has been dropping, so we want a decay factor, so we want 1 minus 3%, so I'm going to write 3% as a decimal, that would be 0.03, and that gets raised to the x. So I could write it like this, I can enter it in the calculator like this, or I can rewrite it as 15,500 times 0.97 raised to the x. So let's go to the graph. Okay, so I entered our graph, but I don't see it. Again, we're going to need to play around with the menu. If we go back here, we can see that we need to get up to at least 15,500, and then it'll be dropping from there. So let's change our window. Let's see, maybe 25 years out in the future, and I want my y maximum to be 15,500, or I'll just make it 16,000. Alright, so there's my graph. And now again, if I want to see when is the function going to be, let's see, the question is, use the graph to predict when the population will drop below 8,000. Let me show you one other way to get that. If we want to know when the population is going to drop below 8,000, let's enter a new function, Control G, and just type in 8,000. We're going to get a horizontal line, and where they intersect here, that's what we are interested in. So I can even find that intersection point by doing Menu, Analyze, Intersection. That was Menu, Analyze, Intersection. And I'm going to tell it lower bound here, upper bound here. It's found an intersection for me at 21.7, 8e plus 3, which would correspond to 21.7 years and 8,000. So the population of the town will be down to 8,000, 21 years, 21.7 years in the future. Okay, so that's it for this video. Make sure you've taken good notes. Make sure you have all these good examples from the graphing calculator on. And one more thing, I think we're going to have a visit from a little pet friend. Okay, I just wanted to show off Charlie. This is Charlie. He's a guinea pig, and he's sweet. Have a great day, everybody.